But yes, we are now back to our old setup. So, yes. Veterans Day was fun. I flew back that day, so it was alright. It was a long day, but there was very few people at the airport here, so that was nice. Okay, so I'm still getting used to the dry air here compared to the air there, so it's kind of weird. Great. All right. So the first thing that I wanted to announce is the extra credit points. So I went ahead and if you already have enough points, go ahead and redeem them. If you haven't already, if you don't have enough points, but you think you're going to get enough points by the end of like, what is it, the week of the 29th, then wait, so you can get that. If you don't think you're going to get enough points to get to that tier, then I did unlock another tier that's lower, the 100-point tier versus 300-point tier, which I will bring up in a second. But so you can redeem that, but only redeem that if you don't think you're going to make it to the higher one. And that last week I'll go ahead and release smaller tiers, like maybe like 50-point tiers or something, so that you can get all the points maximized. I did change the points though. The 300 points are for 202. You get 600 points. So for those of you that already redeemed, I changed your extra credit from 300 to 600 points. So so you should see that. You should see that up reflected there on Canvas if you already redeemed them. That it should go up from 300 to 600. And there was only about 4 of you, I think, 4 or 5. But yeah. Out of stock, check back later. Maybe that's because there's like a limit of how many people can redeem per day, which I don't know why I set that at some point. It like broke. Let me go ahead and check that. Limit redemptions per stream 10. Did like 10 people just redeem immediately right now or something? Is this what happened? Nope. So I don't know. Does it say that right now if you try to redeem? Which one did you try to redeem? Skip reward queue. I don't know. But yeah, I don't know. Require viewer, skip rewards, cooldown. There's no cooldown, so. Yeah, okay, so you guys are able to redeem them. Okay, cool. So, there we go. Nice, awesome. Okay, so then anyways, as I was saying, if you got them, redeem them. If you don't got them, but you think you're gonna get them before the end of the last week, wait on that. Otherwise, there is the lower tier to redeem, and that'll be good to go. And yes, if you redeemed, send me a message on Discord or email and include your name and the class, because there's also 202 that I need to keep track of. And when you do that, then I'll know who to award the points to. So, and make sure, I guess, 3 things. Include your real name, and then your your Twitch name, so that I know who is who, especially when we got multiple people redeeming. And then also include the class. So, for example, you can say, I am John Wick, I am in CS302, and my Twitch name is Dog Lover 123 or something. Okay? So something like that. Okay? What do you mean if you're unsure? Well, I mean, if you just wait. Just wait. If you think you're gonna make it, just wait and redeem later. If you got the points now, redeem them now. If you got them for the higher tier. So okay. Other thing is that I believe the ARNAP extra credit has finally been posted. So if you haven't gotten points for that yet, and you did it, then contact the TA and forward them the confirmation email that you get when you do the survey, so that we can locate you. So yeah, there's that. And finally, we got the data thing. I think these are all the extra credit things, right? I mean, well, the tries and all of that do with the TA. You know, I see someone said that they have a very nice grade right now, but then again, I guess you gotta wait till they grade the second exam, because that's probably gonna like lower your grade. Well, actually, yeah, even if you have a perfect grade, it'll lower it because of the averaging out of the points. So, yeah, that's actually the way it works, right? Because I mean, the math. Oh, well, actually, no, because it's weighting it. So if you got a perfect grade on the first test and you got a perfect grade on the second one, it wouldn't lower it. Only if you get less than perfect, then it would lower it. So I think that's how it works. I don't know. Canvas is interesting, but okay. All right, so let's get into class material now. So last time, it kind of feels dark. Yeah, that's fine. Last time we were talking and introducing graphs. So we said that a graph is made up of vertices and edges. Vertices are the dots or the nodes, the loop bubbles that you want to call them, and edges are what connect these vertices together. So they're the lines, basically. And those lines may or may not have a direction to them. If they don't have a direction to them, we call that an undirected graph or an unordered graph. If they have a direction to them, such as little arrow, then it's called an ordered graph or a directed graph. Okay? In terms of notation, when you're writing a undirected graph, you are going to just go ahead and put curly braces and put the pair of vertices that are connected with that edge. When it comes to a directed graph, then instead of curly braces, you're going to put parentheses. So for example, this is an edge going from vertex C to vertex B. Now, something to think about here, because that term was brought up last time, if I recall correctly. Isomorphic, I think it was a term, I can't remember. But let's talk about this. So this here, this list of vertices and edges, represents this graph, which looks like a Z, right? However, I could do the exact same graph in terms of vertices and edges, but it may look different. So let me show you what that would be like. Well, here's a very simple example of that. Let me just take the graph as is, copy paste it, and then just flip it upside down. And maybe take this one and like move it. All right, hold on. Like that. And I know the letters are backwards and whatnot, but just imagine the letters are fixed. The point is that this graph and this graph are technically the same graph. In fact, if you do the vertices and edges, which is what defines a graph, they are equal. Therefore, we define that it's equal. However, visually they look different. In fact, another way that we could do this, just an example of that one, is so we have A, we have B, we have C like that, and then we have D, right? So that's what we have now. So suppose that I go ahead and I get rid of C, and I do it like this, just because why not? Sure, crossing lines is not ideal. If you really don't want to cross the lines, then I could go ahead and do come on, there we go. Do something like that. But what I'm trying to get to is that even though they visually look different, they're the same graph. And that's what we care about. So just be aware of that. That two graphs may look different, but they may actually be the same, assuming that they have the same vertices and the same edges. Now, if I say, okay, I'm going to rename vertex A to vertex W, and I still have the same graph, yeah, sure, they're kind of the same graph, but technically they're different because they have different identifiers. It's like, it's like variable names. You have different identifiers, but it could be the same code, So that one, it's a little more iffy. Kind of depends on what you define as the same. But what I'm saying is that you know, even if they have the same identifiers, the graph may look different just because of the way it's drawn, okay? So that's hard. And there's some problems that you're going to see if you take the math classes, the 351 or whatever, that talk about like, okay, given an X number of vertices for a graph, are you able to connect the graph without having any lines crossing each other? So for example, if I said, okay, go ahead and draw this graph, but and add a connection between A and D. Can you do that? And I could say, sure, I could do it like this. Okay, no lines are crossing. And then I say, okay, cool. Now I want you to do a line that connects C to D. And you're like, okay, no problem. I can do that over here. Fine. And then go ahead and do one that connects B to A. Well, I could do that here. And I could do something from A to C. And like I could try and figure out ways that these lines don't cross each other, just looking at this. But trying to do this like with an algorithm is very hard, okay? Especially if you can't do curved lines, you have to do straight lines. Then some graphs you can't even do it in the first place. And so these problems are like the Hamiltonian path and the Euler bridges, I think they're called. So you get to explore them, and they're from a complexity point of view, they're pretty hard. Okay, so that's all I'll say about those for now. That's more of the math class, but they're very interesting. Anyways, so that's what we said. And the last thing that we did say was what a path is. And the path is basically a sequence of vertices that are going to take you from a start to an end. And if the path exists, we say, well, there is a path between vertex like A and B. And then we define that path by showing the sequence that you have to take, which is basically like you giving directions to somebody, like how to go from like my house to your house. Well, you got to go this road and then turn left and turn right, go here, go there, go there. That sequence of instructions that you're telling somebody to go somewhere, directions, that's your path. And the way we define that is by just listing the vertices that you have to stop at. So we're saying go to W1, W2, W3, all the way till they get to the objective. Okay? And as long as you have those edges that exist, then we can say that there is a path. The path can contain one vertex, like, you know, bam, you're there, or it could contain 100. You shouldn't have duplicate vertex in your path, because that means you would be going back in circles to the beginning, right? Just FYI. Okay, so today we're going to be talking about adjacency matrices and adjacency lists, and what they are ways of representing a graph for a computer. Now, you can represent them with pointers, and sometimes that is a convenient thing to do, just like a linked list style, or like a tree, which you do. But as you saw with trees, you can also represent them with arrays, right? Like how we did heaps. And so when it comes from like a computational perspective, when you're trying to quickly access all the entries of a data structure, you can do that with arrays, right? But you can't do that with things like linked list. So for example, an ABL tree, if you implement an ABL tree using pointers, and I say, yo, give me all of the contents of the tree immediately, you can't do that quickly. You have to traverse a tree to like do a traversal to extract items, right? Whereas with a list, such as with a heap, with an array, such as heap, you got all the data immediately. You can immediately say, okay, who is like the parent of this or the child of that, or give me all of the nodes back immediately. You can do that quickly, right? And so adjacency matrix and list are kind of like the array version of how to keep a graph versus like the pointer version, which is like how we did like ABLs, okay? However, before I show you adjacency matrices and adjacency lists, I do want to finish a couple of other terms that I didn't get to last time. Those terms are things such as cycles in a graph. So we're going to go ahead and kind of do those first. Okay? So the first one, which I just mentioned, is a cycle. So let's talk about what a cycle is. Cycles only really apply to directed graphs. So those are the ones with the arrows. And what it looks like in simple terms is when you have a graph that allows you to revisit a node that you've already seen when you're walking around it. So for example, this is a cycle in a graph, because if I have a point here that I'm starting, I can use this connection here, I can use this connection here, and I can use this connection here, this edge, to get back to the beginning. So that is by definition a cycle. That is like what I said, you know, giving directions to somebody, you don't want to give them a cycle because they're just going to go back to where they started and waste time. Now, a graph could have other things in it. So, for example, here's other parts of this graph. And it might not be so obvious that there's a cycle. Obviously, here I will show you that there's a cycle because I highlighted and I started by graphing that. But if I get rid of this and I ask you, show me all the cycles in this graph, then there may or may not be more than one. We know that there's a cycle here because we saw that. Is there a cycle here? I forgot to draw a little bubble here, but there isn't a cycle anywhere else that I can see because here, oh, well, this needs an arrow. There isn't a way to go around, so there's no cycles there. No cycle there. Yeah, that's the only cycle that I see in the graph. Cycle detection is not easy. If we get to it, which I don't know if we will, then I'll show you an algorithm for detecting cycles. That is not like just trying to do like greedy algorithm to try to get this, okay? And you can use sets for that. But I don't know if we will get to that. That's one of those extra things. But I do have a video on that. Okay? So cycles are a issue when you're doing some graphs because when you're looking at a graph and you have like a massive graph, you can't look at it all at once. So you're almost like a person driving with a, but you can't really see the roads because they're really wiggly and whatnot. And so it's like you're taking a road trip and you start here and you're like, well, I need to get here, but you don't really know how to get there. So when you get at the intersection here, you're like, well, I only have one way, which is here, so I'll go here. But now here I have two ways, this way or this way. And if you can't see that far, you're like, well, it's a 50-50. So you take this one. And then you take this one and you're like, oh, snap. Dead end. That's not where I wanted to go. So you have to go back. Then you try going here. And you're like, darn, I already been here before. So this is not very nice for that kind of stuff. Cycles can cause you to just keep going in circles, especially if you don't remember you already been there, right? It's like almost like you're lost in the forest. And you might be going in circles and you don't know it. Okay? So anyways, just wanted to explain that terminology. We'll come back and revisit it again if we get to that algorithm. But this is what is known as a cycle. And it only happens in directed graphs because by definition, in an undirected graph, here's an undirected graph. Because it's undirected, that means that all of the edges are like bidirectional. So you could go back and forth. So that means that you have cycles like all over the place. The entire thing is a cycle. Everywhere's a cycle. Like, cycles everywhere. Okay? So because of that, it's basically pointless to think about cycles in undirected graphs. Okay? So now that we talked about cycles and that they only exist in directed graphs, there's a special kind of graphs, that interest us. And those are graphs that don't have cycles. And they go by the name of directed acyclic graph. Abbreviated as DAG. Just acronym. Okay? So we've actually have seen these directed acyclic graphs because it turns out that all the trees that we've been doing are technically directed acyclic graphs because normally when we're drawing our trees, we have the node, the parent node and the children node, and you only draw one arrow basically. We're going from the parent to the child, or vice versa, whatever you want to represent it, but you only go usually in one direction. So it turns out that the hierarchy itself is a tree, and I'm going to go ahead and just copy paste it. This is all the stuff that we have looked at, or we will see for the remainder of the semester. So overarching this whole group of algorithms with trees and graphs and everything is just graphs. From there we have the division between whether the graph is directed or undirected. For undirected, we see them, we talk a little bit about them, but we don't really care much about them. Direct is what we're interested in this semester. From there, we have things like trees. We also have things binomial heaps, which you didn't talk about, but in general, the binomial heaps are like normal heaps, but we looked at our binary heaps, but binomial heaps can have more degree, so like more branches than 2, so like 3, 4, 5, and so on. You'll get to see them in the analysis of algorithms. But anyways, within trees, we saw different kinds of trees, such as binary trees, which was the main focus. We did talk about unary trees, which are just linked lists. And then, of course, we looked at just binary search trees, AVLs, binary heaps, and so on, right? So we kind of worked our way from like here, down, and now we're going up this tree to talk about these and a little bit of these, okay? So, full circle coming together kind of thing. All right, that's another term that's important. So directed acyclic graph. One other thing to talk about is when you're talking about paths and somebody mentions the length of a path, that simply means the number of edges that you need to get from your starting node or vertex to your destination node or vertex. So the number of edges in the path from start to finish. Okay, I'm not gonna write the full definition. You get it. Just kind of simple thing. Okay, so like if I say like, give me the path between vertex A and vertex S, and these have some other names to them. Then you can say, well, there exists a path that goes from A to T to W to S. There is also a path that goes A to T to B to W to S. Technically speaking, there's also a path that goes A to T to B to T to B to T. You could repeat this like 50,000 times, right? Because that's a different path. It's unique because you're just going different amount of times to the same places. But we don't really care about those, and you don't really want to put that kind of stuff in there. So don't repeat nodes, because that means you're dealing with cycles, okay? Just wanted to make you aware of that. And then we say the length of the path is how many edges there are. So there's an edge here, edge here, edge here, right? So that means that this path has length of 3, whereas this path has a length of 4, right? So this one is basically that. As you can see, there's 3 lines. And then the other one, this one, is basically that, which has 4 lines, right? And they're different. And there's no cycles in either one. Obviously, you can think that the top one's probably better, right? We'll talk about that when we talk about the shortest path algorithm known as Dijkstra. That'll be the last topic that we cover from the graphing group. Okay? So that's just the number of edges in the path, and again, it's going to become important to us because we, Google Maps. You want Google Maps to give you the fastest route, right? Not like the slowest route. So we care about things of path, a number of edges, because that usually adds to time. We visit this in a second when I talk about weighted graphs. But first, let's talk about one term that I used earlier, and I've used in the past, and I think I told you what it is, but let's just make sure that we fully define it, and that's degree. Degree is what you all want to get, right? I think. I don't know. Sometimes I question whether you want them or not. But yeah, in this case, degree, though, is not the definition that you think about. Degree is the definition that we're going to give it is that when we have a vertex and you have edges coming out of that vertex, we call that the number of edges. We call those the degree of the vertex, okay? So for example, we have a vertex, and this vertex is connected to 2 other vertices. We say that this vertex here, so let's give it a name, vertex A, has a degree of 2. Okay? Think about trees. Our trees had a degree of either 0, which is like a leaf node, 1 when there was a single child, or 2 when there was like 2 childs, right? So we could say that all the trees that we looked at had a degree of 0 to 2. Range of that, depending on what node we're looking at. Because we have talked about directed graphs and undirected graphs, we can define whether things are coming into the node or out of the node. So we call them the out degree and the in degree. So for example, for a directed graph, so this is undirected, of course there's no lines, so we just count them all. If we have something like this, then we say that the out degree of this are the lines going out. So those two. So we say that there's a 2 for the out degree. And then for the in degree, we only have one line coming in, so we say 1. Okay? But if this was an undirected graph, then it would just look like this. Right? So we would say the degree of that is just 3. So it matters whether the graph is directed or undirected. Okay? Think about like a congestion point of view. We have a ton of things coming in, but only one coming out, like in traffic-wise, that's going to be congested, right? It's like a freeway that like goes from 5 lines to 1. So degree matters for those kinds of things. Notice that navigation system to do fastest route, shortest route, and equal route. Well, the way that matters is you have to define time. So when you're talking about fastest route, you're talking about time. When you're talking about shortest route, you're talking about distance. And then equal route, which probably would be some balance between distance and like time, because you know, if it's a really small distance but it takes like 10 hours because of traffic, you're going to pollute more, I guess. So that one's a little fancy. But for the first two, you are going to define, when I get to weights, this will make sense, but you're going to basically define whether an edge takes longer than another edge. So I'll come back to your question when I talk about weights, which is what somebody else said on the chat. Yes. So, but before I get to weights, I want to finish this degree stuff. So, let's see, I got a definition for a cycle. I want to share this definition of a cycle. I think you already got the. Here's a nice little term. I don't really see it used a lot, but I'll share it. I don't use it at all. If you see the term digraph, that just means directed graph. So just FYI. But I don't really use this term. Yeah, that's all I'll say about that stuff. I already defined a cycle, right? If you want a formal definition of that, is where in a directed graph, there is a path with a greater length than 1, because otherwise you're just not going anywhere. But yes, you're just standing in the same spot is technically a cycle, where the first and one of the vertex in the path is the same, or first and last. So yeah, okay. So two other terms that I want to talk about are strongly connected and weakly connected graphs. Okay, so a strongly connected graph is a graph where there is a path from a vertex A to some vertex B, and from a vertex B to a vertex A, whenever A and B are connected. So in layman terms, what that means is that if you're looking at a graph, we consider a graph to be strongly connected if you can get from every node to every other node, some way or another. Okay, so if you say like, okay, I can get from this vertex to any other vertex in the graph, and any other vertex can get to you, then I would say that graph is strongly connected. There may not be a direct edge from like, say A, B, C, and D. There may not be a direct edge from A to B, but there is a way to get there, right? In fact, there's two ways. You can go this way or you can go this way. So as long as there are connections that allow you, or edges that allow you to get there, you're good to go. Obviously, when you're looking at a directed graph, this is not as easy to see. Okay? Weakly connected is like, okay, suppose you have a strongly connected graph, but that graph is undirected. But now let's take the same graph and make it directed. Here. Let's just copy paste it. But this time it's directed, and maybe there's arrows here, and there's an arrow here. Something like that. And so now you're like, okay, well, I can get from C to B to D to A, no problem. But from B, I can't get to C. I can get to D and A, but I can't get to C. So then I would say that this graph is weakly connected, because in the directed version, it's not connected. Like, it's not strong connected. But if I took this graph and I remove all the arrows and made it undirected, then I would consider it to be strongly connected. Therefore, that's why it's called weakly connected. Okay? So, let me know if that does not make sense. Alright, in the meantime, let's talk about weights finally. It's like weights, right? Okay, so with weights, so far we've been talking about edges, and we haven't really defined, like, you know, suppose you have the following graph. We have a starting node, and we have a finishing node here. And we have A and B as well. It's directed graph. And I say, I would like you to tell me from start to finish what path I should take that's quicker. Well, right now, you know, we can think about length of a path, and we can say that, yes, from S to F, there is a path that will take you through A. And this has a length of 2, because there's 2 edges. And there's also a path that takes you through B, and there's also a length of 2. But the way we draw the graph make it seem like the edges are the same, and they are. In fact, if I drew the same graph like this, that's the same graph. And because this graph is, even though it's directed, but it's what we consider unweighted, which means there's no weights associated, both paths are considered to be fair game. Like, they're both at length of 2, they're both equal. And if, like, we're looking at roads, and I said, hey, which path would you like to take to get to your destination? Well, this looks shorter than like that. But if we're not looking at the weight of something, then it doesn't matter, okay? And both graphs are identical. So far, like I said, all that we've been looking at is considered to be unweighted. So what are weighted graphs then? Weighted graphs solve this issue that we have now, that we have these 2 paths that really, if you're looking at it in a scale format like this, that one of them looks obviously shorter than the other one. So weighted graphs work by adding a value associated with its edge. So just a number. So for example, let's say this is 3, 1, 5, 7. What I've done now is I've added these weights to my edges. What I'm saying is this is the cost to traverse this edge. It's like these are toll roads, and this is how much money they charge, expensive roads, in dollars, to actually go from one vertex to another. So one point for the other, okay? So I'm saying if you're starting from S and you would like to go to A, it costs you $3. And from there to go to F, it costs you $1. So a total cost of your trip is going to be $4 if you take the SAF path. On the other hand, if you take the SBF path, that's going to cost you the total of the 2 edges, which is 5 plus 7, right? So that's going to be $12. Which one would you like to take? Well, unless you like paying for fun, then you will take the cheaper one, right? You take the one that costs you $4. Now, of course, maybe it costs $4 because that is like the cheap road versus like some nice, really nice highway or something, right? So this comes down to the question that was asked earlier. When we're carrying out navigation, we don't always just talk about the fastest route. We also talk about the shortest route when you're trying to save gas, I guess, or also if you want a toll-free route, things like that. This is where weights can come to your play. You choose what weights you want to give to a graph and what they represent. And that allows you to then decide which path you want to take. So when we visit Dijkstra's shortest path algorithm, we are going to be looking at a weighted graph, and we're going to be taking that into consideration. Now, again, the weights can be something as distance. They could be time. They could be an aggregate of multiple factors together, such as like the eco thing. But that's something that you decide how you want to weight that. And then you make that the standard. The algorithms only take, once you decided some quantitative way of measuring these edges, then they'll tell you which is the shortest path because it has the lowest amount of weight associated to that path. Okay? What is this on traffic incident? Well, the algorithms allow you to recalculate based on where you're at. So the algorithms expect the weights to be the same. If the weights change, then you recalculate the shortest path based on that. So if there's a traffic incident, then I presume that, like, let's say that this weight of 1 becomes 10. Well, when you get to A, you can recompute that if you choose, but that's going to be computational intensive. So that's not necessarily some problem that you would run into. It just costs time to compute. But yeah, so that's what weighted graphs are about. They allow you to basically put a weight to an edge, which now, I'm still, I could still do the same graph like this, by the way. I can still say 3, 1, 5, 7, I don't particularly have to make the edges longer because they have a bigger weight associated to it. Otherwise, I would run out of paper when trying to do things to like scale. So you still see a graph like this instead of seeing something like this, which is why it's more important, again, to just look at the numbers and not the actual way the graph is drawn. The way the graph is drawn can be very, very misleading. In fact, I could have drawn the same graph here, but like chosen these to be the heavyweights on the top and the longer lines to be the lower ones, and they might be misleading. So like, suppose that I did this. Or here, I know what I can do. It's the same graph, but here I'll just switch the letters, yeah. And I said this is 1, and I think this was 3. And just switch these. There we go. Still the same graph. It just looks different. Like now it looks like, oh, well, the top way should be faster. But no, all I did is just like flip the way I drew the graph. But the graph has the exact same weights, the exact same vertex names. Everything is the same. So don't trust the way the graph is drawn. Trust the numbers and the letters. Okay, so trust that definition of G is equal to, equivalent to the vertices and edges. Okay, all right. So that is your weight system. If you say your navigation to avoid tolls, for instance, would you attach a Boolean flag to the edge cases? No, you would have to, well, if you're trying to avoid certain edges, then you just remove them from the graph. So you don't consider them to be edges, right? So for example, if you have 3 paths to get from your house to the airport, and one of those paths involves a toll, and you don't want to consider that path, then you remove one of the edges from that path that it has the toll in it. And then when you're trying to find what the shortest path is, because that edge is no longer present in your graph, then you no longer consider it. So if like I don't want to consider this path here, when I'm trying to compute the shortest path, all you do is you simply remove the path. So you don't, sure, you could do like a Boolean saying is the path active or not, but from like a mathematical point of view, what you do is you say that path is not, that edge does not exist. Okay? So yeah, you could also do that. Like you could also like make it infinity or something, but it's, you know, it's better to just not have something. I mean, that we'll talk about that actually, because that becomes an issue. Like, you know, how do you represent when you do an adjacency matrix and you're trying to list a path that does not exist? You can't just write on a computer and say, well, there's no path here. You got to pick some value, right? You got to hard code some value for that. And yes, you usually do something like infinity. But then again, infinity, you don't have infinity in C++. You don't have infinity in Python. Like, well, maybe NumPy or something. But like, you don't have anything like that. So you got to pick some value. And if you pick 0, that's bad. Because that's like instant travel, right? That's like teleportation. You don't want to put that there because that definitely screws up shortest path. And if you put a negative number, that's even worse. Now you're time traveling. You got there before you started. So what are you left with? You put a really big number that doesn't overflow, right? So yeah, like hard code, yeah, max value, exactly. So usually that's what you tend to do. That's what I recommend you do for the assignments too, I believe. So yeah, but like I said, you know, we haven't quite gotten to the X-ray yet, but we will. But first, let's talk about adjacency adjacency matrices and adjacency lists. Okay. I think in LaTeX, because of the 301 class, they're using LaTeX to code their assignments, to write their paper. Okay, so let me just show you an adjacency matrix, and then let's talk about it. Okay. So again, the idea is I want to represent in the computer a graph, okay? And in this case, I would like to represent the following graph. We're gonna go ahead and do an undirected graph for now, but we can update this to be directed in a minute. Okay, so this is the graph that I got. I can draw circles if you'd like, but that's it. All right. So one of the two ways to do this is with an adjacency matrix. An adjacency matrix is just going to be a table, so a 2D array in C++, that contains whether an edge exists or not. So what you do is you just literally code a 2D array, and for the dimensions, use the number of vertices that you have in your graph. Obviously, you can't label them. You know, they're going to be index 0, 1, 2, 3, 4. So you just got to remember that 0 represents 1 or 2. If you really don't like that, you can use an enum. Voila. You got yourselves letters. Okay, it doesn't matter what you pick internally to do. You know, here I'm doing A is A and goes first. That doesn't matter as long as you can translate that and say, well, whatever is here represents this node here. You have to have a way of doing that. Again, an enum or just hard code it doesn't really matter much. Okay, so when you do that, you have to decide like a start and an end. So I like to just say the top represents the to, and the 1 represents the from. Again, it doesn't matter much right now because this is an undirected graph, but it will when it's directed. Okay, and then you just fill it in. So first of all, we say going from A, what's connected to A? Well, A has 3 connections technically. It has A to C, it has A to B, but it also has itself. And that's just something that you want to keep track of, because otherwise, you know, coding stuff breaks and whatnot. You want to be able to remember that you can go to yourself. Because of that, we're going to put 1s wherever there's a connection, and then we're going to put 0s where there's nothing. Again, you can do 0s now because it's an undirected graph, and it's unweighted as well. So undirected and unweighted. Okay, let's go ahead and also put, what is it, B. There is no edge going from A to D, so I'm going to put a 0 there. Okay? All right, moving on to B. What does B go to? Well, B goes to D and A and C. It goes to everything. It's the popular one, I guess. So then we just basically fill 1 everywhere, right? Because it also goes to itself. All right, we got C. C goes to A and C goes to B, but it does not go to D. So that's going to be 0 and everything else is going to be 1. As you can see, the pattern, all the diagonals here are always going to be 1 because that's just going to yourself. Another thing that you're about to see here, well, you'll see it in a second, but let's first finish D. D only goes to B and to itself. So we have a 1 here. But these two others are zeros. Here's something interesting that happens when you're doing an unweighted, undirected graph. You end up with a symmetry. So if I was to draw a little line here, you will notice that the top and bottom look equal. I don't know, what does that mean, abelian? I've never heard that term. But yeah, you have symmetry. So they're equal, and that's to be expected, actually. In fact, if you want to be super efficient, if you have an undirected graph, you can always keep it in only half of the memory, because the other half will be mirrored because it's undirected. So that means that something that goes somewhere also comes back, right? So yeah, very cool. Any questions about this? And by the way, if you would like to see what the representation of this looks like in terms of like the graph, the math, I have it here. So I'm going to paste it. We have graph with vertices and edges. The vertices are A, B, C, and D has 4 edges: A to B, B to C, D to B, and A to C. But again, it's undirected. Okay? Cool. What if we make it a weighted undirected graph? Well, let's add some weights to this. Let's say this is a 2, a 3, a 4, and a 1. How does that change this? Well, let's try doing it again. Here, let's just copy and paste everything. But let's delete the numbers from this example so that people don't get confused later. So what we're going to do is we're going to update wherever we see a 1. It's going to have to get updated. But also the zeros will get to update it. In fact, everything's going to get updated here. Because now we have a problem. We have that problem that I was mentioning. What do we put for something that doesn't have an edge? We can't leave it blank, right? We can't do that on a computer. Like, what does blank even mean? Like, there's going to be garbage value, right? We can't put null because that's just a 0. And 0 means that there is an edge. And in fact, it's not just any kind of edge. It's an instant kind of edge, right? In fact, I would say that for the ones that you're going to yourself, yes, you're right. You put a 0 because it takes no time. It's instant to say, okay, I'm going to travel of all places in the world. I'm going to travel to exactly where I am. Here I go. Bam. It was instant. Why? Because I'm already here. Well, within the world, right? Because technically we're going, what, like 220 kilometers per second over like the Milky Way core. So we're moving plus whatever the rotation of the sun is. So we're not in the same spot that we were, but at least relative to the Earth, we are in the same spot, right? So within that point of reference. So that's why we think about that as being an instant. Okay, cool. We can also go ahead and list all 4 edges that we have here. By the way, when you're trying to add a weight to something like this, you can put a comma after the thing and put the weight. So you could say something like A, comma B, comma like 2. I can even do that. You could also put it before. I don't know. There's a lot of notations. That one I'm actually not too familiar with, like what the standard is representing a weight in that. But just be aware of that. They'll put some kind of number somewhere in there. But anyways, let's go ahead and fill this in now. All right, so let's go ahead and fill in A. So A goes to both C and B. So we know that it goes to C with a weight of 2. So we're going to put that there. And then to B with a weight of 3. But then what do we put for D, right? There is no path. We can't put negatives, like I said, because if we do, then that technically means that we're traveling in time. That means that we have arrived there yesterday. That's really bad. That's going to really screw up your shortest path, because if anywhere in your graph there's a negative weight and you're trying to go from anywhere else to anywhere in the graph, then your graph algorithm is going to try to go to that negative weight, travel in time back a few times to gain some time, and then go find the location and then be like, yeah, I got there yesterday. Why? Well, I went to a different part of the universe where there was a time machine. I took that time machine to go back in time so I could arrive faster here. So algorithms are going to get messed up. When you get to 477 and they talk about ancestral algorithms, there is more than just the extra shortest path. In fact, the extra shortest path, I believe, doesn't work well with negative values, but there are others like Bell and Ford and whatnot that I think will work with negative values, aka time travel. Okay, so no time traveling for this class. So negative values don't really work out. So as somebody suggested at some point, you do just use an infinity for that. And then coding wise, you use max value. And hope for the best that nowhere in your code an edge legitimately has max value, because then that's gonna do weird things. Okay, so yeah, now that we know how to do that, let's finish filling this up. So B goes to A, B, C, and D. It goes to A with a weight of 3. It goes to C with a weight of 4. And D with a weight of 1. C goes to D with nothing, so we're going to put infinity. But it goes to A with a weight of 2. And this should be 4 because it's a mirror, right? Yeah. So we can, without doing D ourselves, we should be able to just mirror it from here, which is infinity, 1, infinity. But if you see, that's actually what happens, right? Because D only goes to B with a 1, and these are infinities. So there you go. That's how you represent a weighted, undirected graph. Okay? Infinities for things that for edges that don't exist. 0 for yourself, and then the weight for whatever it be. Technically speaking, you can represent a graph with negative edges this way. In fact, you should. You are able to. But like I said, we don't really do that in this class. But just beware, if you do have to handle time traveling, Adjacency Matrix got you. Okay. Finally, let's go ahead and look at the version of this that has a directed component to this. Okay, so we're going to the same graph again, but this time we're going to make it directed. So the difference being that we are going to use parentheses. I don't want to draw that. It's too much work. Well, first let's actually define where we want to do this. So let's use the same weight, but let's just put some arrows. So maybe put an arrow there, maybe there, maybe there, and let's do that one there. Yeah, I like that. I'm happy with it. Okay, so now that we did that, so let's go ahead and draw these edges. So let's just delete it. It'll be faster if we just do it from scratch. So C to A goes C to A with a weight of 2. We got C to B with a weight of 4. We have B to A with a weight of 3. And then we have D to B with a weight of 1. Okay, so let's go ahead and represent that here. So again, we're going to erase everything. I'm going to leave the, I should have left the centers. I'm going to leave the infinities because those, we know for sure we don't have those edges. And then these should still be zeros. So the only thing that's going to change are any of those. And there's only going to be 4. There should only be 4 numbers in here now instead of, will be double of that, which would be 8. And the rest should be infinities here, aside from the selves. So let's do C to A2. So C to A2 means it's going to go from C to A with a 2, which does represent that. Next we have a C to B with 4. So that's C to B with 4 right here. That's also present in the graph. Then we have B to A with a 3. So that's B to A with a 3 there. You can also see that in the graph. And finally, D to B with 1. D to B with 1. Okay? All the other ones don't exist, so we can go ahead and put infinities for them. And there you go. That's all there's to it. Now it's not symmetric. So now you actually need to store the entire thing. You can't do that optimization of storing only one triangle of it. So, yeah, and there's going to be more infinities. Okay? So, as you can see, this is a good way of representing graphs. From a space perspective, let's talk about space complexity. How long does it take to store, how much does it take to store this? Well, it's going to take b squared, right? So it's going to take the number of vertices squared because you have a table that is vertices by vertices. So length times width of a square, area is just square. So that's where I'm getting the b squared from. From a accessing point of view, so from the time complexity point of view, this is instant, it's O of 1. Because if I want to check whether an edge exists and what its weight is, if it's weighted, I can do that immediately because it's an array, right? So I can access any element of the array immediately. So it's O of 1. So it's fast in terms of access time. So in terms of time, it's fast. And in terms of space, it's not bad. I mean, b squared could be worse, right? However, well, it's not bad per se. As you can see here, when you have some graphs that don't have a lot of edges, we have a lot of infinities just there. In fact, look at this graph. Like, pretty much half of this graph is infinities. Could be optimized. Like, wish we could somehow optimize it, right? So let's talk a little bit before we talk about optimizing, which we can do with the adjacency list. Of course, there's going to be a cost associated to that, pros and cons. Let's talk a little bit about what I'm saying when I mean a graph doesn't have a lot of edges. That has a name, and that name is known as a sparse graph. A lot of terminology to it. So, what is a sparse graph? Well, there's no well-defined method that I could find. Like, I Googled at some point and I could not find like a consensus on what is defined as a sparse graph. But the general consensus is that it's a low edge to vertex ratio. What I'm saying is a graph that has, if it has like 20 vertices and it has like one edge, that is definitely a sparse graph. But if there's a graph that has literally like all possible edges in the graph, it is definitely not sparse. Okay? So what is the opposite called when a graph is like full of edges? Well, we call that one a dense graph. We will say that's a high edge to vertex ratio. So when you have a sparse graph, an adjacency list is not going, adjacency matrix may not be the best way of storing the information because you're gonna end up allocating like a bunch of space you don't need to. Now you could use like a jagged array, but you risk accessing something that doesn't exist at some point and bad things happening. So it's not ideal per se. Now, if you want to know more about like what will be defined sparse and dense, like I said, there's no defined value, but I'm going to go with something like 30%, anywhere from 30 to 50% of the edges possible. Okay. What I'm saying is, if you have a graph with 3 vertices, then how many edges can you have at most? You can only have at most 3 edges, right? What about here? Well, at most you can have 1 edge. However, technically speaking, if you consider the directed graphs and you have them in both directions, right? So in this case, it would be 6 and 2. What about when you get 4? Well, with 4, you can have 4, but then you can also have the crosses, right? And then when you get 5, you can have all of those, but then you can have those, you can have those, you can have one here, 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 and I think those are all of them, right? Yeah, I think so. This goes up pretty quickly. As you can see, it's going up pretty fast. There's some math property, I don't remember it right now, but yeah, it goes up fast, okay? And so when you're looking at the number of vertices versus the edges, if it's relatively low, then you call it sparse, okay? But again, there's no defined number like we're saying, oh, okay, if the ratio is over 30%, it's going to be for sure not sparse and dense. It's got a leeway, okay? So a dense graph, adjacency matrix is just it, because it means that most of these are not going to be infinities. Most of them are going to have some weights associated to it. It's the way to go. In fact, even if it's undirected, it's still the way to go. Just do the optimization of splitting it in half and only storing the top triangle or the bottom triangle. But when you have a graph like the one that we actually have, where it looks kind of sparse to me, although this is a pretty small graph, so this is actually one of those where, like, I don't know, it's kind of 50-50. But if you do have a graph that is sparse, then adjacency matrices may not necessarily, they work, but they may not necessarily be the best way of storing it. For that, you can use an adjacency list. So what is an adjacency list? An adjacency list is another way of storing the graph. Again, these are ways you store it, because in the computer you need to figure out a way of actually storing the information, right? You can't just tell it yeah, it's a graph and here's a drawing of it, memorize the computer and work with it. Actually, you could probably write a program that could do that at some point. It's not too bad as long as the graph is legible, but it's that's not really practical when you're trying to draw a graph with 1 billion different vertices, like a Google Maps or something. So we are going back to the same example that we had before, undirected. We're back to the undirected method because it's a simple one. So it means we have A to B, we have B to C, and then we have D to B. That D looks weird. And then we have A to C. Now this may look different than the other drawing, but remember, the graphs can look different, but they're still the same. In fact, it doesn't look that different. You just have to use your imagination. Okay? So the way you do an adjacency list, again, let me just show it to you, and then we'll probably do more of it next class because we only have 10 minutes left. But, for now, I'll just give you this example. So you're going to have, again, your little from and to. And in the from, you're going to list all of the vertices that you have. So again, this is, if you're thinking like an array, you could do this with an array, but you could also do this with a linked list. Kind of. Think of not only linked list, but like a hash table. Remember with hash tables with separate chaining, where you have your one-dimensional array, and each one's a linked list so that you can list multiple things if there's collisions. That same data structure is what you can do for this. So you have an array that is an array of pointers, and then you store edges there, basically. So in this case, A is going to go to only B. Oh, did I screw this up? Oh, I did screw up, because this last one, D, does not. I said D goes to B, but then I said Yeah, this one's wrong. It should have been A to C. So that. There we go. Okay, fixed. So yeah, okay. So then in this case, what does A go to? Well, A goes to B and it goes to C. So you just list all of the vertices that something goes to. B goes to pretty much everything, A, D, and C. So we list them. You don't have to list them in alphabetical order, but you know, you can if you want. C goes to A and B. And D only goes to B. So that's it. This right here is storing the same information as cursor 0, 1, this one. Here's the optimization. Number one, you don't need to keep yourself because that's obvious and you don't need to put the space. Number two, you could optimize this by removing duplicate stuff. So like A going to B and C means you don't really need to put C and A, C to A, B. But you can leave it there if you want. But finally, this will take less space to store than it will take to store an adjacency matrix. Let me show you really fast. Let's skip forward to the weighted one. Let's use the weighted directed one. This one. Let's store that one in an adjacency list. So A, B, C, and D. So if we want to store the path from A goes to nothing right now. So yeah, nothing goes there. So we leave that empty. B goes to only A, and it has a weight of 3. So you can put a pair like this. A, 3. When you're coding this, you can make that be a linked list that contains two values within the node. You know, it contains the vertex name and the weight. Or a tuple in Python if you're using Python, but you're not in this class. For C goes to A with a weight of 2. And it goes to B with a weight of 4. And finally, D goes to B with a weight of 1. And there we go. This is our adjacency list. So look how small that is compared to how big this one is. Or sorry, not that one. This one. It's much more efficient, and you don't have to worry about the whole infinity stuff because you just don't list that edge there. So the infinity issue goes away with like edges not existing. You don't have to worry about like keeping yourself because you know that A goes to A always. You can hard code that, and so you save space. Now, how much space do you actually save? Well, I have it at the top here as a reminder. When you're coding this and you're implementing it, in terms of space complexity, the space that it takes to store an adjacency, oh, I flipped those. Those are flipped. Darn. Glad I cut that. Here we go. So the adjacency list is going to be the number of vertices you have plus the number of edges that you have. So that's going to be your space. But here's a little asterisk, you know, the footprint text. This is what they get you. Your time's going to take a toll. It's no longer O of 1. Why? Because just like a linked list, if I ask you, is there an edge between C and B that exists and what is its weight? You can't just like immediately get it because like it's just like when you're doing separate chaining in your hash tables, right? Sure, you can immediately hash or get to C's index, so you can immediately get here and query this data. But the A and B right here is basically a linked list. So you have to potentially traverse this entire list. And technically speaking, that can be as long as the number of edges that you have. Because imagine you have a graph where like it literally looks like this, like a star. So you have a dot, and then you got a bunch of lines coming out, and each of these is going to a vertex. And they're all arrows going out. If you do an adjacency list of this, let's just say that this is A, and then you got B, C, all the way to like Z. And here you got them all. And all of the rest of the stuff is empty. And if I ask you if an edge exists, but let's say there's one of them that's not, all right? And let's just say we're looking for that one. And we're going to say if there is an edge between that and A, or A to that node. You're going to have to look through the entire list of edges here until you say there isn't one. That's worst case scenario, of course. Worst case scenario is going to be looking through that list of number of edges, which is not good, right? It's not good. TS. So from a perspective, you can think of like an O of n sort of linear time sort of time complexity, which is not bad from like compared to like sorting or something, but it's still not O of 1. So you lose that quick access. And remember, you might be doing this for like multiple, because you're trying to build some path or shortest path or whatever. You have to do a lot of these lookups. So it's going to take a toll on that. So don't just say, oh, it's linear, let's just stick with the adjacency list. No. Take a little more time before you make that decision if you were implementing something like this. Adjacency matrix, I would usually say, is the way to go. Again, unless space is a concern. And if it is, well then you're stuck with like adjacency list. But my recommendation is just always go with adjacency matrix. Okay? So it's good to know both, and you know, that's why I show them both, because I don't want you to end up seeing an adjacency list somewhere out there, and then you're like, what the heck is this? Like, what is this way of representing a graph? Now you know. Okay? So the short cheat sheet is use adjacency matrix when you have a dense graph or you need that quick access time and you're willing to sacrifice that OB squared space. Use adjacency list when you have a sparse graph and you care more about saving space at the cost of potentially some time. And technically, if it's a sparse graph, there's low amount of edges, so even that O of E time shouldn't be too bad, technically speaking. As for sparse versus dense, it's up to you to make a decision what you consider, but I think you kind of see it. Edge to weight ratio of over 30%, I would say it's not sparse, but some people will say 50. What else do I want to say? I have a bunch of other examples on the lectures from other years, but for now, this is interesting. Very C style. I would use max value, but if you want to just be old school, that will give you the biggest number that you can get as a hard-coded constant value. So define. Just define it as infinity. You can use that. It'll work fine. Yeah, that's it. That's all I want to say. So next class, we are going to be looking at depth first search and breadth first search, which are two algorithms which are kind of like your traversals. If you think about like traversals and like trees. In fact, level order traversal is a breadth first search traversal. And then the other ones you did like in order, post order, and pre-order are sort of like a depth first search traversal. So yeah, you know, we've seen traversals for trees. Now we're going to see traversals for graphs. So that'll be the job of next class. I'm very happy I was able to cover everything I wanted, and it's a lot of good information. Some of it is probably review if you've taken your math classes, and if not, then when you take your math classes, then hey, you'll be doing great because you know this stuff already, right? So yeah, but I do have to get it because there's no prerequisite to know this stuff for the class, so that's why we covered it. Okay, great. Well, thank you all for watching, and don't forget to redeem this credit. Don't forget to send me a message. I will not respond right now because I do have the other class back to back, but around 7 p.m. when I get finished with both classes, then I will respond to every single one of you after I add the points. And then make sure you check. And if you don't see the points being added, then tell me, okay? So don't forget to do your assignments and everything. Thank you all for watching, and I will see you next time. Your weighted graphs.